Hi, I'm Brooke Ablis. We are Team ODDSat. That stands for Ocean Debris Detection. You might also know us as GodSat. The requirements for our mission started off with that the Cubesat should boot up on power startup. We would confirm this by the yaw values when they start printing. The Cubesat should identify the poster board by positioning of the Cubesat in relation to the orientation and heading, and should take pictures of each of the poster boards with the Pi camera 3 times each orbit for a total of 9 images. We would verify this by having north printed out when the Cubesat reaches the north position, and pic taken would be printed out in the next line. Pic taken would be printed out 8 more times for a total of 9 times total throughout all of the orbits. The Cubesat should then process the images that it just took and save the enhanced and cropped images with the statistics. These statistics include the percentage of board that has plastic on it and the percentage of each color of plastic relative to each other. It should use processing tools such as OpenCV to facilitate functions. These functions include contour, mask, find area, grayscale, etc. We would verify this by printing out the following lines. Enhanced image JPEG, contour cropped image JPEG, etc. The files are saved in Pi and should be accessible in the Pi. Next, the Cubesat should save the original images along with the statistics and enhanced and cropped images to a local device. These files are going to be saved on the local device. Images and statistics should be uploaded to Google Drive for remote members to see. And we would verify this by having the files uploaded and visible on the bwsioddsat@gmail.com Google Drive. This account is accessed by all members of the team instructors. The Cubesat is also built so that the materials are intact and Pi camera and battery and IMU are accessible. We can verify this, of course, by being able to freely move around the fully stable Cubesat unit. The camera and IMU are fully functionable. Battery percentage should be showing at all times, and the cable ports need to be easily accessible.
Hi, I'm Neri. This is the ConOps. So first, during pre-launch, the Cubesat will be powered off. We set up the poster boards, one of the setup options that the instructors provide. In startup, the Pi is triggered on the boot on start script, and we elevate the Pi to waist height to start our orbits. When it is launched, the IMU is activated and it starts finding the orientation and yaw values, and all subsystems start running. In science mode, the Cubesat will go into data collection, where it waits for the IMU to reach and align with the magnetic north yaw value, and it will take the first picture. Then the timer will be set every 20 seconds to take the preceding 8 pictures for a total of 9 pictures. In idle, the image processing step will happen. This will take about 2 orbits. The Pi processes all 9 images, and it will enhance, crop, and determine percentage of plastic per board, percentage of each color, and also each type and color amounts. Continuing in idle, it will downlink all these statistics and images. This will take about 3 orbits, and via the Bluetooth, the ground station or the local computer should receive all of these. In image sharing, which will take about the last 2 orbits, the computer would automatically upload these images and statistics to the Google Drive, which all the members have access to, and they can then save the best ones with the best qualities and confirm some of the statistics. This is all a linear progression. This is a system level block diagram. The solar array should feed power into the battery, and the battery will then feed power into the Raspberry Pi. The Raspberry Pi will then send power and commands to the IMU, which will then send information back. Similarly, we'll send power and commands to the camera, which will then also send information back. The information, which would be ideally the images and statistics, will then be sent to the ground station via Bluetooth and then uploaded to the Google Drive.
Hi, I'm Madeline. As you can see here, we have the mechanical layout both in CAD drawing and in real life. We wanted to position the battery so that it was not hanging above the Raspberry Pi because it was quite heavy and we worried that Velcro would not be enough to hold it in place. So we managed to rotate the Pi and position the IMU in a way that gave the battery a full half of the Cubesat. We also were sure to position the solar panel opposite from the camera so that while in orbit, the camera could be pointed towards the Earth while the solar panel was pointed towards the sky taking readings. Originally, we positioned the IMU so it was hanging from the top plate of the CubeSat. However, that messed up the magnetometer readings, so we had to last minute change it to the bottom.
Here's the co-design, which are the main subsystems of our CubeSat. First, we have ADCS and picture taking. The Pi gets the input from the magnetometer, which is aboard the IMU. Before the code is run, each user runs a program to determine which direction is magnetic north. Then, when the orbit begins, the Pi waits until the magnetometer reading points to magnetic north before taking the first photo. After that, the Pi waits 20 seconds before taking a second picture. This works because the first picture is aligned with magnetic north and the others are spaced so that the CubeSat passes over them on every 20 seconds.
For the image processing step, this combination of codes will take images that the camera has already captured before and will enhance them. This includes brightness, contrast, sharpness, etc. This enhanced photo will then be put into the contour and crop script, which will then contour the image and crop it based on the biggest contour, which should be the poster board. After this is done, the image will then be straightened in case the angle of the frame is not perpendicular to the poster board. The outputted image should be of an enhanced, straightened, and cropped image of just the poster board. This will then be inputted into the statistics script, which will determine percentage of plastic on the board, percentage color relative to each other, etc.
Hi, I'm Graham Wilson, and I was in charge of Bluetooth. So once all the pictures are taken and processed, the RF COM code kicks in. All the images will be sent as text files containing bits about the image, and then they will send that to the ground station via Bluetooth. The ground station code needs to be run on the ground computer. It connects to the Pi over Bluetooth, and as it receives the incoming bytes as text files, the ground station converts them into JPEG images and then uploads them to Google Drive. Once they're in the Google Drive, then they will be decorrupted and viewable by the team.
Hi, I'm David Wong. I'll be talking about the code design for a CubeSat. In terms of the backbone, we built an architecture for the system that connected each subsystem into one code. So there's basically one background script that runs all of them as modules. The main code sets up like the orbit rounds and makes sure each poster is captured through the IMU, processed with the image processing, and then sent over Bluetooth to be uploaded to Google Drive. There's also a launch script that starts up when the main code is run. When the Raspberry Pi is powered on, it will automatically run the main code. So this will allow for hands-free orbit with no manual steps.
So overall, how did the flight go? Well, although every team member was able to successfully take 9 pictures, only 2 were able to upload to Google Drive. Both of those ended up being on Windows, but that was just a correlation. So, however, the uploaded files were corrupted and contained no data, which was a major problem. So definitely need to fix that. The launch script was also not fully automated, which caused some team members to have to manually start their Pi on power up.
We did learn a few things we would have done differently, either given more time or if we restarted. For one, we need to devote plenty of time to testing. We basically did all of our testing in the 30 minutes before the flight started, which was less than ideal. We also needed to give more time for integration. We found a lot of troubles with like getting the exact definitions into the right places in the code just because everybody wrote their pieces of code slightly differently. That sort of segues into the next one. We needed more communication. We had some troubles with repetitive variable names, which messed up our code quite a bit. Also, we ran into some issues, as I said earlier. The IMU was mounted upside down, and that gave a lot of issues to the person who coded the ADCS. We also would like to build in plenty of backup systems, just in case, say, several of the pictures are taken crookedly or it doesn't find north perfectly the first time, because our IMU did have quite a large range of error.